All right, so this is the first topic in the chemical kinetics chapter, and here they have us doing a couple of things for this particular problem. The first thing they have us doing is determining whether this chemical, and in this case this is ethanol, if it's being created or destroyed by the chemical reaction. So if I look here at this graph, I see on the y-axis I have molarity or concentration, and on the x-axis seconds. So it's molarity and seconds here on the x-axis. So this is telling me that as time increases, as the seconds go by, the concentration of ethanol decreases in this vessel that this reaction is occurring in. So this tells me that ethanol is being destroyed because the concentration is decreasing with time. Okay, it's being consumed in this reaction. Now the next two here, they ask us if ethanol is being created or destroyed, what is the rate at which it is being created or destroyed 120 seconds after the reaction starts. So what they're asking us to do is to find what the notes in your in the lecture PowerPoint call the instantaneous rate. Okay, the instantaneous rate. Now if you check the notes in the PowerPoint, it says that in order to find, let me write what it's called, instantaneous rate. In order to find the instantaneous rate, you need to find the slope of a line tangent to the curve at that particular time, at that particular instant. So how do you do that? Well, when you're looking at the problem, if you find this tool right here, you see this tool? That darker line is the curve, and this lighter blue line is the line tangent to that point on the curve. So this is our curve here. Let's just imagine this is the same problem. And they said at 120 seconds, I hit this button, I'd find the point on this curve that aligns with that time. So 120 seconds would be over here. I'd find that point that goes down to the corresponding time, and then it gives me the line tangent to that particular point on the curve. So again, if we look at our notes, it defines instantaneous rate as the slope of the line tangent to the curve at that point. Okay, if this is the point, and if this were 120 seconds, then this is the line tangent. It touches right there on that point. So I just need to find the slope of this line, and the slope of this line would give me the instantaneous rate. So I hit this button, find the time within the corresponding point on the curve, and then you get the line here. So you click right there, you get the line, and in order to find the slope of that line, well, what is slope equal to? Rise over run, right? So you take this information from the graph. So remember, we want the slope of the line tangent to the curve. And what is the line tangent to this curve? This line. Okay? So in this case, what's my rise for this line? Or the y-axis, the y-intercept. It is 2.004. Divide that by your run to get slope. The x-intercept is 1910 seconds. And in this case, the instantaneous rate for 900 seconds would be, and I'll just write it here as a decimal, 0.0010492, and I could put this in scientific notation as 1.04, but if I want two significant digits, I just put 1.0 times 10 to the negative 3, and the units are ATMs per second. Now, some of you may say, wait a minute, the slope of this line is negative, right? So why isn't there a negative sign in front of this? That's because rate cannot be negative. Rate is going to be reported as a positive value. So even though the slope of this line is negative, we're going to report it as a rate, as a positive quantity. Okay, so this is telling me that the pressure on this reaction vessel is decreasing by this much per second, and this is the rate. But I know it's decreasing because I'm looking at the data here, right? And it's being consumed, okay? But my rate will be reported as a positive value always. So that's in this case, okay? So I just did this little example. So let's go back to our information, and I want you all to do the exact same thing I just did with the instantaneous rate, okay? So because I don't have the tools to get the exact values here, right, the exact values, it's best that you do it, but I show you how to do it with this template here, okay? So now let's do the average rate. So it says if ethanol is being created or destroyed, and we know it's being destroyed, what's the average rate at which it is being destroyed during the first 120 seconds of the reaction? So this time, what they want us to find is not what the instantaneous rate is at 120 seconds, and in this example, we went with 900 seconds. They don't want the instantaneous rate at that particular point in time in the reaction, but they want the average rate over the first, they say 120 seconds. So for us, it'll be over the first 900 seconds. Okay, so again, they're not asking for instantaneous rate at this particular point. If for instantaneous rate, we use the slope of the line tangent to that point on the curve that corresponds with that time. Now they want the average rate over a period of time. In this problem, it is 120 seconds. In our example, we're going to do it off of the first 900 seconds. Okay, so what do? Well, to find the average rate over a period of time, what I'm going to do is I'm going to divide the change in pressure here, or it could be concentration, by the change in time. And I'm still going to use rise over run just like I did last time. So in this case, what time period are we looking at? For this example, we are looking at the first 900 seconds of the reaction. What was the average rate for the first 900 seconds? Okay, where's the starting pressure at time 0? It's right here. And they give us that y-intercept. It's 2.583 on this plot. Okay, at the end of 900 seconds, what is the pressure? Well, here's 900 seconds. The pressure is now 1.06. Okay, and the change in time is starting time 0, ending time 900. So this is what we're going to do. I want the slope of this. That's going to give me average rate over this period of time. Okay, so to find the slope, again, of this section, I'm just going to find the change in pressure, and I'm going to divide it by the change in time. It's almost like in math where you had to find the slope and you had 2 data points. Let's look at it like that. So here's data point number 1. Here's data point number 2. And do you all remember this? y2 minus y1 over x2 minus x1 equals slope. All right, let's use that. So what is y2? 2.583. So 2.583 minus 1.060. I'm going to divide that by x2, which is 900, minus 0 is 900, but I'll write it out. 900 minus 0 is going to be 900. And so this gives me a slope of, and you have to be careful, keep everything in parentheses. If you want to put this in your calculator all at one time, you need to open a set of parentheses, place this, close it, and then hit divided by, and then you need to put the second function in parentheses. That'll keep your order of operations separate. If you don't do that, you may get the wrong answer. So what I get when I do that is a decimal again, 0.0016922. They want us to round to 2 significant digits, I believe. 2 significant digits. So I'll put it in scientific notation. I would put 1.0 7 times 10 to the minus 3. And the units are ATM per second. You could also type the answer in as 0.0017. Both of those answers should be acceptable. Okay, so just to recap, what we did was we found the instantaneous rate, and in this case it was at 900 seconds, by finding the slope of the line that just touches that point. This is what we call being tangent to this point. Okay, and then we found the average rate over the first 900 seconds by finding the slope of this line, and we used this to do that. Okay, again, I didn't work out this exact problem because I'm not using the tools that you have in ALEKS where you can get very precise values. It's best for you to use the tool because any numbers that I come up with on this iPad will just be a rough guess. Okay. And finally, when you place your answers here in the blanks, make sure to also put your units. Okay, and if I check here, my units are going to be molarity per second. Molarity per second. Okay, so type the value in, whatever number that is, to 2 significant digits, and then a space, and then molarity per second.